name's Alan Cantle, and I'm presenting on the OCP High Performance Computing SubProject. I'm going to give you an update. So if you're new to this and you're not familiar, I recommend you also go to the Introduction to OCP HPC at that YouTube link, and that will give you a lot more detail than I'm going to go into today. But first, I'd like to start to take a step back as to what we've been quite radical in what we're doing in OCP HPC, and it's really driven with this energy-centric computing perspective in mind. And so I wanted to give you a better understanding of some of the conclusions we've come to in terms of how to proceed forward. So energy-centric computing, really we all know that data movement consumes the most energy in computing, and it really provides zero utility. We obviously want the computer, the processors to do the work, not spend time moving data. So over the years, I've come to these three guiding principles. One, minimize power when the data is idle. Two, don't move the data unless you absolutely have to. And when data has to move it as efficiently as possible. And our guiding light is the value is in the data, and the processor cores can often be effectively free, so distribute them freely. A good success story is mobile phones, everybody knows. That's very application specific, seriously constrained real estate, and the goal is ultimate performance per watt, so that you can fit within the very tiny 1 watt power envelope. The way they have achieved this, and we all know what Apple have done, they've got domain specific on silicon. So that's many heterogeneous processors that are very efficient at their particular function. And they've done that very specifically for all the phone's needs. And it's an amazing feat. But basically, this is the best you can do. This is the best optimization in a monolithic die. And they even have very ultra low power interfaces to the neighboring components, the very few neighboring components. So that's what you can do when you've got something in a mobile world and you've got the volumes to drive it. But we're taking a leaf out of that book, heterogeneous domain specific architectures, and we're doing domain specific on package with chiplets. The high bandwidth memory is probably the most successful integration of chiplets into a package with processors, but everybody's looking towards multiple heterogeneous processors in a similar way to the way Apple have done. But these are done at the chiplet level, so you can mix and match that for your particular application for the most efficient implementation. You'll be hearing from OCP's ODSA shortly. And they're focusing on chiplet standardization. Very excellent working group. I thoroughly recommend them. So, but this does give you a very constrained physical composability. You know, there's quite an expensive packaging job by the experts, and the ultimate goal is really the best performance that you can achieve. But your performance is really constrained by power ultimately, and as was just said in the previous presentation, NVIDIA I think have the record with their latest H100 is in the 700 watt region, and we've been talking about trying to get to a kilowatt region in these modules. So that's the constraint of as far as you can really take it. But what about system level energy-centric computing approach? Well, I don't think that the idea here is we believe there are better ways to do this. So, but what we see is supercomputers of today. The top left is the Summit machine from 2018, and the bottom left is the Frontier machine just being installed now. And they're heterogeneous in a node, and with a mix of GPUs in both of these cases and a couple of CPUs. So they're very similar architectures. Again, we're going heterogeneous. I was going to say proprietary. We've got the HGX from NVIDIA. I've just heard that they're opening that up, so that's great news. Another good example is Google's TPU for AI machine learning applications. Very, very, very custom. And you've got this more general purpose, this desire for us to have software composability, so we can pick the pieces that we need and compose them quickly into a particular application. But in a disaggregated rack. But is that really energy efficient? You've got to move that data an awful long way. And so I think there are some fundamental flaws in this thinking. So this is what's driven our thinking on this, of making things much more flexible. So I tried to say, how can we see the energy that's being consumed by the I/O? And so I've tried to do this, and I'll take any input to improve it. But we talk about moving data in energy terms in picojoules per bit. So for example, a terabit per second, you just multiply it at a picojoule per bit I/O would give you 1 watt of power consumption. So that's just the basic equation. So I've drawn this diagram. You can see that we've got data movement in energy is shown in red. So all of the I/Os that are going on, obviously things like NICs and PCI switches often are just I/O handlers. But I want to emphasize a few specific pieces here. First of all, the HBM, you can see this chiplet connection is half a picojoule per bit, compared to a standard interconnect is in the region of 5 to 10. So there's a 10x order of magnitude gain by bringing the memory on package. But not only that, the actual memory itself in the 3D stack is only 4 picojoules per bit for this HBM stack, compared to a 34 picojoule per bit for a memory DIMM, a large memory DIMM, albeit at 256 gigabytes against the 16 gigabyte HBM. Optical modules, they're typically in the 10 to 20 picojoule per bit. So obviously it still makes sense to stay in the electrical domain until you exceed that by adding repeaters, etc. So this is just where we're at today. And finally, in the SSDs, this was a little bit of an interesting one for me. You think that if the data's idle, you'll burn no power, but actually the controllers in these SSDs do burn quite a bit of power if they're on the ready to go, and their idle power is similar to DRAM. And more interestingly is when you do access them, they actually do consume more power than your DRAM. So that's an interesting thing to bear in mind. But suddenly it allows you to think about things from an energy perspective when you start to draw block diagrams like this. So hopefully I want to refine this more, and I'll take any input from people. So let's take a look at the frontier node from an I/O energy perspective. Again, it's a fixed heterogeneous node topology. So what we mean by that is you've got the CPU and you've got a dedicated set of wiring to the 4 GPUs with Infinity Fabric, and that's the wiring diagram on the right there. And the CPU has its 8 memory channels. But and you can see there's two Infinity Fabric links from the CPU to each GPU. But what if your application, if you analyze your application, you said, oh, I need the bandwidth of 6 XGMI links, Infinity Fabric links between my CPU and one of the GPUs. Well, sure enough, you can do this with this architecture, but you're going to have to route 4 of the lanes through 2 of the other 250X GPUs. And that's a very expensive, wasted energy way of getting that, versus being able to directly connect 6 lanes from the CPU to the GPU. And that would be much more energy specific, energy saving. Also, what if your application needs deeper and more memory bandwidth? You know, HBM's great bandwidth, but not very deep. DDR is very deep, but not very good bandwidth. But what if you do need more? Well, unfortunately, that decision's made inside the at fabrication time of the processor. The designer decides how many local memory channels and how much I/O they have. So OCP HPC, we've got a system level and energy-centric architecture vision. So what I'm going to show here is an abstract view of where we would love to take the industry, but it needs a lot of collaboration. We'd like to tightly couple compute with all and any memory types in a pluggable 3D fashion. So we're taking this heterogeneous, this compression of the technology to the system level, not just silicon and packaging. And we'd start with, in the middle, we've got many terabytes of memory. It could be non-volatile, persistent, or file system storage memory. And you've got a high performance processor still connected, the big heavy lifting processors. But we want the lowest picojoules per bit, lowest power energy between those two, and the lowest latency, and as high a bandwidth as you can from a pluggable interface. Inside each of these memory devices, you would have distributed tiny little embedded processors that can actually deal with some compute and avoid moving the data across these more power-hungry interfaces. So it's you're distributing the computing there. And then we want to efficiently share that processor's near memory with other processors in your system when you come to a big system. So we have a high bandwidth memory pooling data plane fabric. And this is the point where we would ideally hand off to silicon photonics. We'd have a shared memory buffer through a shared memory buffer interface. So there's two ports on the memory, one to the big high performance processor and one to the distribution fabric. It's not a processor interface. So this is a vision of where we'd like to get to. But obviously there's a lot of things that need to change here in the industry for this to happen. But we can still build the same architectural approach to take our first step in the system level architecture towards this vision. And that's what we're doing in OCP with our high performance compute module called the HPCM. It's inspired by the OAM module and it leverages EDSFF media technology. So the key thing is it's modular, flexible and composable, and it's protocol agnostic at the module level. So we can run anybody's bus across these modules. We don't want to pick a winner on protocol technologies. But the key thing is we can mix and match memory, storage and I/O with all of the interconnect. Obviously it will depend on whether a processor can support it or not. An FPGA for instance is a Swiss Army knife, so you can switch between different interfaces. And you would choose that mix depending on your application need for the best performance at the best power point. I'm just going to flash this up so you see the physical look of the module. Again, go back to my general overview presentation to get a better understanding of this. But on the left, you can see it's like an OAM module with a powerful processor on the top, but we've replaced the mezzanine connector with module connectors and cable connectors. And on the right, we've given an example of E3 modules, NIC 3.0 modules, and cables plugged into the module. Again, I stress for you to watch the main presentation to get a better understanding of this. And if you look at this, it looks very much like the block diagram. I believe we can get to those energy targets with this physical architecture. Okay, so what are we actually doing in the OCP HPC update? Well, we wanted to choose an application, and we found out really that AI, this was one application that needs low latency high memory bandwidth and a tremendous amount of capacity that HBM can't give it, and DDR can't give the bandwidth. And Berkeley Rise Lab have shown these numbers. That's a bunch of graphs showing basically this need. So we said, well, okay, this looks like a good application that we could focus on. But at the same time, we want
just time check. You got another 2 or 3 minutes.
Yeah, okay. I've got a couple of slides. That should be it. But we want to do we wanted to replicate an HPC node. Can we actually rebuild an HPC node as well with this architecture? So we looked at the Summit machine. That's made up, as you can see there, with 6 NVIDIA GPUs and 2 IBM Power 9s. We wanted to put it in the OAI chassis. So we'd like to house this in the OAI chassis as one implementation. And so we would design two HPCM modules, one for the IBM Power 10 and one for Xilinx Versal. And we're working in collaboration with AMD and IBM on these modules. And we would attach a lot of OMI memory to the FPGA modules. So we've got up to 38 terabytes. This is where it's different. It's the same architecture, but it's much more memory, and it can go at 5.8 terabytes per second. So this is of interest to the AI community. Just to look at the modules are simply the processor chip and the interconnect, and obviously you've got the power supplies and some sideband, which I'll touch on. IBM's is very specific, so the modules you plug in need to match IBM's needs. On the FPGA, it's the same module. It's the FPGA connected to the same types of connectors, but you've got more configurability in the I/O because they're programmable, software programmable I/O. And so we're building these two modules. That's our starting point, is trying to bring these two modules to reality. And finally, a critical part of our project here is the board management controller and sideband management. There's an awful lot of that in there, and we want these modules to boot independently, but we also want them to be designed to integrate in with the DCSCM security module infrastructure that will be housed in the OAI chassis. And so here Lattice are contributing some of the serial tunneling protocols that will allow for an efficient implementation in the design, and they're helping us with this. So in closing, that's what we're up to. We are a sub-project where we're focused on creating an energy-centric computing architecture that is open, modular, flexible, and composable. And my call to action is, we're an unfunded working group. We're looking for volunteers, anybody that can bring some ideas and help to get us bring these modules to market or to prototype would be great. And we're also looking for funding sources to help accelerate the progress. There's my contact details below, and also a few links if you want to find out some more information. So thank you very much.
Thank you, Alan. Anybody have any questions for us?